Okay, welcome everyone for attending today's seminar. It's not Euro time because we have a time difference between two sides. We have to pick up time, which is comfortable for both sides. I hope the time didn't interrupt your time to go, interrupt your plan to go home or for dinner. It is great opportunity that we have Dr. Sudhanshu Shukla from IMEC today to give us the talk. Dr. Shockley is a senior researcher at Inter-University Microelectronic Center, or IMEC, at Belgium. He got his PhD from Nanyang Technological University, Singapore in 2017. And during his PhD, he was a visiting researcher scholar at Lawrence Berkeley National Laboratory and the University of California, Berkeley, US. And after his PhD, he joined the laboratory for photovoltaics at the University of Luxembourg as a postdoc researcher, where he developed the high-efficiency wide-bandgap CIGS solar cells. After that, he joined IMEC as a senior researcher, where he's currently leading a research activities on the electrochemical fuel conversion. In 2022, this year, he has been awarded the Marine Curie Fellowship by the European Commission. His research focuses on developing chalcopyrite and emerging materials for their application in photovoltaics and photoelectrocatalysis. His talk today is with the title of What Limits the Performance of Wide-Bandgap CIGS Solar Cells. Now, I would like to acknowledge Dr. Maharsh for proposing and inviting Dr. Shukla. Now it's over to you, Dr. Shukla. Thank you for your time today.
Thank you very much for the kind introduction, Kaivan, and I'm also thankful to Mahesh for inviting me here. It's always a pleasure to talk in SPREE seminars, which I have been a great admirer, of course. So today I will be talking about CIGS. In all the talk today, when I say CIGS, don't get confused with selenium. So there won't be any selenium today. So if it is CIGS, it is pure sulfide CIGS. So what limits the performance of wide-bandgap CIGS? When I say wide-bandgap, it's about 1.6 eV bandgap that I'm referring to. And the work that I will show today has been mostly performed at University of Luxembourg, where I was working before joining the IMEC. So without further ado, why are we doing what we are doing? To understand that very briefly, I don't need to emphasize enough. I'm talking to a solar PV audience or energy conversion audience. We are dealing with a terrible climate emergency, and the numbers are telling all the story. So we have all the bad numbers that you can think of. We have the highest CO2 concentration in 2 million years. That's the highest so far. Sea levels are rising. The Arctic Sea is at the lowest level, and we have unprecedented melting of glaciers in 2000 years. And what it has done, it has triggered a non-linear catastrophic processes all over the planet, resulting in extreme heat waves, very heavy rainfalls, droughts, and forest fires, and ocean acidification as well. Only this month, I'm coming from India, and if you look at the temperatures this month, it went as high as 48 degrees. So this is something we really need to worry about, because we are feeling the effect of it every single day. So this snapshot that you see is from the IPCC report, and what it tells us, what should be the response of this emergency? The response should be obviously shifting from fossil fuels to renewables as quick as possible. So that's the new future we are referring to, renewables. And that brings us here to the future, which is about carbon neutrality and circular economy, where solar is going to play a big role, because it's a massive contributor to the renewable energy. So solar is going to be in the center for quite some time. And this picture that you see right here, it presents you the roadmap of the future, where you actually use the CO2 emitted from the industries or the daily usage. You can convert them into chemical feedstock and to the fuels using the renewable itself. So at the center of it, you have electrolyzer, which actually turns the CO2 to the fuels of interest, for example, methanol, ethanol, etc., which you can then use and then capture it back again. Where this energy is coming from, basically it comes from the sun, and we have the solar PV. Either we can directly use the solar PV, we call it PV electrolysis, or we can do it in situ like photoelectrochemical approaches. So solar is going to be in the center, not only just for the electricity, but also to convert solar to fuels. And as a soothsayer, Edison already said that I put my money on the sun and solar energy. He said it way back. So he realized long back that this is the future that we are heading towards. So this is what pretty much I am doing at IMEC at the moment, involving in the PV electrolysis and PEC part. But before that, I was focusing on solar PV, even I'm focusing now. So I will be talking about solar PV today. So in general, we are talking about converting solar energy photons to electricity, which means we need to see first how the solar spectrum of the sun looks like. So it looks something like this. So this is the spectral radiation of the sun at the Earth's surface. And we have to use it basically. So we need solar absorbers. And these absorbers, we know they are semiconducting materials. And depending on their band gap, they can absorb the light of particular wavelength at or above that energy. So for example, if you take a semiconductor with a certain band gap, which is depicted on the right, and if you then shine the photons, blue photons or higher energy photons, this is going to get absorbed, and a lot of those photons will be simply thermalized. Basically, all the electrons or holes that are excited into the excited states, they will relax back and lose their energy in the form of heat. So this is like a heating loss. So all the heat will be transferred to the lattice. This is called thermalization loss if the photon energy is higher than the band gap. But if you have the energy of the photons at the longer wavelengths, meaning the energy of the photon is lower than the band gap, then the light will not be absorbed at all. That is the loss because of the incomplete absorption. So as you can see, if you take the photon of energy higher than the band gap, you will have a high energy of the photon, but then you will not absorb enough photon. So you will have a good voltage kind of, so you will have higher power because the energy of the photon is high, but you will not have sufficient photons to absorb. On the other hand, if you take a band gap material, which is lower band gap material, it is going to absorb all the photons, but the energy of the photon will be too less to do some work out of it. So, and the VOC, the maximum open circuit voltage or the maximum power resulting to that, is not the conduction band and the valence band difference. It's basically the difference of the quasi-Fermi level splitting, which is basically the internal photovoltage of a semiconductor. So as you can already imagine, that you need some sort of a compromise in the band gap. It shouldn't be too low, it shouldn't be too high, it has to be somewhere in between. This is how the curve then eventually looks like. And this is given in the classical Shockley equalizer limit, that if you pose conditions, the thermodynamic restrictions, which takes into account the finite temperature difference between the sun and the solar cell, the angles, etc., the number that you get for a single junction absorber is about 33%. If you take a material of 1.35 eV band gap. So that's the optimum band gap value we are talking about. The good thing about Shockley equalizer limit is it not only just tells about how high you can go in numbers, it also tells you, the very assumptions tells you how to break that limit. So to break that limit, as I said, this is for the single junction. So what you do, you go for the tandem systems. Basically, it's a dual junction that I'm referring to, or it could be multi-junction, for example, where you have a higher band gap material at the front, which absorbs the blue photons, and all the wasted photons which are not absorbed by this high band gap material will be absorbed by this bottom low band gap absorber. So this is an example of a dual junction tandem solar cell. Multi-junction tandem solar cell today, as of now, they are about 49%, and they are the highest efficient solar cells on the planet right now. So we will not be talking about multi-junctions, we will be talking about dual junctions. So why do we care about tandem solar cells? What's the bottleneck here when you want to make a tandem solar cell with two junction, basically, or what is limiting us? So as you know, this is the color plot which tells you that if you choose a top cell material of a certain band gap, and if you take the combination with a certain bottom cell band gap, the maximum you get somewhere with a bottom cell band gap of about 0.95, which is 1 eV close to silicon that you use. and also CISE, for example. Also in the case of two-terminal solar cell, where it is depicted on the right, when they are monolithically integrated, then the wide band gap or the top cell has to be about 1.6 eV. So the good thing is that we have the bottom cells that we know today. They are very efficient. For example, silicon, or if you're talking about thin films, they are CIS, copper indium diselenide. But what we are lacking today is the top cell, which is wide band gap, or so to say 1.6 eV to 1.7 eV band gap top absorber. Of course, we have perovskites and there is extensive research going on, but the problem that I want to emphasize today applies to perovskites as well, as you will see in the next slide. But this slide tells you that basically by using copper indium disulfide, you can obtain this band gap 1.6 to 1.7 eV by introducing, so this is the GGI, which is in copper indium gallium sulfide lattice. If you incorporate more and more gallium, you can increase the band gap from all the way up to 1.5 to 2.4. And with very low quantities of gallium, and I'm talking about 0.1 to 0.2, you can get this desired band gap. And this is something very nice as compared to selenium, because for selenites, the same band gap you will obtain if you will have gallium more than 0.3. And that's where the losses kick in. If you look at the photovoltage deficit in selenide absorbers, it's mostly when you have the higher gallium, the photovoltage deficit kicks in, and then you are limited by that. But here in this case, you have an opportunity that you can get this band gap even at low GGIs. So you have more window to play on gallium, which could be useful for other applications. For example, for wideband, let's say for photoelectrochemical cells, for example. This brings me to the outline of the talk. So I'll be talking about pure sulfide and why the efficiencies of sulfide is low as compared to selenide absorbers. So I have categorized in three parts. One that deals with the bulk defects. So the defects that are somewhere in between the band gap, these are killer defects. And I'll also tell you that why anti-side deep defects are very crucial for disulfides and how you can actually passivate the interface. And when you talk about interface, it's not as simple as talking about the band energetics. There is something else also going on. So even if you have a perfect band alignment, it is not going to solve interface passivation problem. And also some roadmap for the future. How can we move ahead from where we are today? So these are the three different technologies or semiconductors that you are looking at. The VOC deficit. So if you increase the band gap, your VOC deficit increases. This is what it tells you, that you see it doesn't scale. So which means if you increase the band gap, the VOC do not increase linearly, but rather limits itself. Same happens with the selenide, same happens with the halide perovskites as well. Although their origins are different, for perovskites, it's halide segregation and unoptimized contacts. For selenides, it's the gallium, as I just mentioned, the deep defects. For sulfides, we know the least among all three. So if you see the plateauing, it's kind of behaves in a similar way in all these technologies, although this plateau is shifted up or down, but it more or less, it's true that when you increase the band gap, the VOC generally does not scale with the band gap. It limits itself. So how to think? So there is something profound going on. There's something common in these different materials, that pretty generic observation. So for that, I will refer it to this nice study, and I would highly encourage everyone to read this one, the Shockley-Reed-Hall recombination in wide bandgap semiconductors. So they become extremely important and limiting factors when you are dealing with wide bandgap semiconductors. But at the same time, you have to be very careful about the interfaces as well, because when you increase the band gap, it's not just the bulk that is giving you the losses, but the interfaces that you need to then alter, because then the electron extraction and hole extraction layers have to be optimized accordingly, which sometimes we don't, because we use the same buffer layers even if the band gap is high. So the interface losses might also be responsible for this plateauing. That's what I wanted to convey. So when we think about photovoltaic deficit, it's basically originating from the recombination losses, and the recombination losses are happening in the bulk, and there could be a bunch of reasons. One is this, we all know, is the deep defect within the band gap, which is like a killer defect, limits the lifetime and is responsible for the carrier recombination. We can have these band tails where then the recombination can occur, and that also can account for hundreds of MeVs of losses. And also you can have potential fluctuation if you have a very high degree of compensation, for example. And one such example is copper poor CIGS selenides, where you do have these potential fluctuations. also in gasterites, for example. And then you can also have recombination at the interface, which could be related to the band alignment, improper band alignment, which is like the cliff type, we call it, negative conduction band offsets. We can have Fermi level pinning. So you have so many surface defect states that your Fermi level is actually pinned, and then your VOC is limited by that. You can also have something very notorious called near interface defects, which is neither explained by Fermi level pinning or this conduction band offsets. This is quite tricky to deal with. And there is another recombination that can happen is at the grain boundaries, which I'm not even putting it in the bulk or interface. I think they lie somewhere in between. So they are both interface and the bulk. If you have a bulk recombination, then what you see is this is the activation energy of recombination. If you derive it from your JV measurements, for example, it scales with the band gap if you have a bulk recombination that is dominating. But if you have an interface recombination which is limiting your VOC, then your activation energies do not change if you increase the band gap, because the defect energy is actually fixed. Then no matter if you increase the band gap, the recombination is actually occurring at your interface. So this is a curve that you get when you are dealing with something that has a bulk recombination dominant here, and when you have interface recombination. And these two you actually see in the case of copper-rich CISE selenites, where we know copper-rich selenide absorbers are actually limited by the interface recombination, so you don't get any change in the activation energies, while copper poor does not have interface recombination or less interface recombination, and the dominant recombination is the bulk. There it actually scales with the band gap. So now, before moving on to the CIGS, let's talk about CIS briefly. What we noticed previously is that if you make pure copper indium disulfide like high quality absorbers, you do get these signatures of the deep defects. So this is the band related to this is the PL that you get close to the band edge, and this deep broad band that you see at the lower energies corresponds to the deep defects. And if you look at carefully and deconvolute it, you get something like two deep defects actually, one close to 1 eV and the other one which is close to 0.8 eV. And this 0.8 eV actually limits the photovoltage in the case of CIS. So even if you passivate it, the next defect that you have to deal with will be this one. So that will then become the dominant factor that will limit your VOC. We have actually suppressed it. We shown it in the previously. So this is in this reference by my colleague, that if you increase the temperature, the growth temperature basically from 550 to 590, the quasi-Fermi levels actually improve. And I'll come to that in later on, what quasi-Fermi level splitting is. And you have the suppression of deep defects. So this is one strategy, how you can actually passivate these deep defects, the temperature, playing with the temperature and the active passivation, for example. And the other thing we have shown recently is that you have near interface defects at the CIS, and no matter what buffer you use cadmium sulfide, even if you use the one that has this spike type configuration, which is the desired one, you still get interface recombination. And the reason is that you have these near interface defects which are causing you the trouble. And that has all led to the highest efficiency so far is about 11 to 12% only. So if you make CIS absorbers in your lab, most probably the numbers will be like 8% to 9% something. That's quite frustrating given the band gap of this material is 1.5 eV. Now you are looking at the CIGS solar cells. So these are some notable references that I am putting it for the perspective here. So if you look at all these, the photovoltages have been close to 900 millivolts, and the efficiency is about 11%. The highest one is about 15.5% from Solar Frontiers in 2016, which it all triggered everything, encouraged everyone to actually think once more about the CIGS after late 2000s. So people start paying attention to this material again. But one thing I want to bring it in your attention, that if you look the optoelectronic quality of this absorber, the record absorber, for example, 973 millivolts VOC, which is quite good. The lifetime is very bad. And here they have shown like there are two components, 0.2, 0.97 nanoseconds. This is really bad. And if you look at good CIGSE or forget perovskites, here the lifetime is very high, but these lifetimes are not at all very good. And also surprisingly, this lifetime is measured at 1.65 eV, while the solar cell performance is of 1.57 eV absorber. So I don't really understand. So with this, there are some open questions that I wanted to address. So what actually limits the VOC? Obviously, by looking at the JV and the PL, one could very easily guess that it's the bulk and interface both. So the question is, how can we passivate it? What are the nature of these deep defects and can be passivated? And how to fix this interface recombination in CIGS solar cells, sulfides again. So we adopted the strategy to this co-evaporation where we can make very nice high quality thin films, but there was a catch, a trick. Sulfur evaporation is not as straightforward as selenium, so it has a very high vapor pressure. So we deployed a custom made PVD chamber where we had this pulsed effusion cell of sulfur where we can pulse it and we can control the sulfur flux as per our will. So we can have a growth in the high sulfur flux and we can have a growth in the low sulfur flux. Although that is not the experiment that I want to show today, but just to mention that we have done a growth in such a chamber where we could actually control the sulfur flux controllably. We adopted this single stage growth procedure where we just evaporate all the elements at once. This is like a single stage deposition process. And we also did 2-stage process to make copper rich CIGS. And we did 3-stage. So we first evaporated indium gallium on the first stage. Second stage was copper evaporation. So when it becomes copper rich, and we monitor it by checking the emissivity of the film. So when it transitions from stoichiometric CIGS to copper rich CIS, then we did this 3rd stage evaporation. So all the films that I will show today will have GGIs in the range of 0.12 to 0.18. So exactly in the range where you can make 1.6 eV band gap absorbers. And also I want to highlight when I say copper excess, it's not the copper rich CIGS, it is CIGS plus copper sulfide that phase segregates. And then you etch it away by using KCN to get stoichiometric absorbers. So all the CGI numbers are actually refers to the absorber as made. So there was no etching, meaning it refers to the amount of copper sulfide in it. So this is the topography and this of the film. So pretty expected. If you look at the stoichiometric composition, it looks quite rough. And at the same time, you have these deep trenches. That's why when we wanted to make solar cells out of it, the cells were mostly shunted because of this bad morphology. And for this copper rich, we anticipated better grown grades. So as you can see, the grains are bigger in the case of copper rich. And then as you move on to the 3rd stage, 3-stage films, as you reduce the copper content, the films looks more or less grainy. And some features starts to appear at the surface also. These steps kind of features. And these are very striking. If you look at all the high efficiency, especially co-evaporated papers, those at least beyond 10%, you do see these features. And these features are also talked about recently in copper indium disulfide study from Princeton, from Professor Kawa's group. And they are speculating a few things, which I'll not go into the detail, but I think you should take into account these fringes as well. When do they appear? If these fringes are coming in your SEM, you notice all this, you're probably going to guess the absorbers are okay for making devices. This is what my experience is with these films. We then move on to quantify the band gap of these absorbers. So we did room temperature photoluminescence. And what you could see, we have absorbers all the way from copper rich to copper poor, and they have a band gap in the range 1.57 to 1.61 maximum. So we not only check the band gap from photoluminescence, we also measure the quantum efficiency of the full device. Looking at these inflection points, they are also they are consistent with the band gaps that we have obtained from photoluminescence. And for one thing you notice here that there is a missing one stoichiometric absorber in this plot, obviously because I mentioned in my previous slide that the cells we tried to make with stoichiometric absorbers were shunted, so we couldn't make a good device to measure a good quantum efficiency. So that's why that plot is missing. These are the shunt paths I was talking about. And then we went to low temperatures to try to investigate more about the defect physics of the material. So what you are looking at right now in this photoluminescence plot, it has taken at 20 Kelvin and normalized to this band edge. What you see, the appearance of these two defect bands, which I have marked as D1 and D2. And D1 is actually as far as 200 millieV from the band edge. Don't confuse this as a band edge, because at low temperature your band gaps might be different than this, which I don't know. So this is roughly 200 millieV far from the band edge, and D2 is actually roughly 500 millieV as far as from the band edge. One could imagine that your quasi-Fermi level splitting or the maximum voltage can never exceed this defect. Unless you passivate it, your VOCs are not going to be any better than 1 point something millivolts. Here also it shows the same thing, that if you reduce the copper content, you see these defect bands disappearing slowly, and also the D1 band remains a bit. So if you plot it in the log scale, you still see some intensity of the D1, but the D2 actually suppresses quite substantially. Then after this observation, we reached out to our colleagues, the experts in University of Cambridge. So they do cathode luminescence, very nice technique to get high resolution spatial information about the recombination. So here they are also normalized to this band edge, and what you see is the appearance of this D1, at least the position where the D1 band that we observed in the PL. So we do see a deep defect signature in PL and also in the cathode luminescence. Then we try to investigate more how spatially how is the spatial distribution of these defects within the absorber. So there is some cathode luminescence mapping that you are seeing in this slide. The top one is actually taken at 1.6 eV, which is the band edge emission, and the bottom one is the luminescence that you are seeing from 1.3 eV, which is the D1 defect that I showed previously. And what you notice here is that as you go more and more copper poor, the band edge emission actually increases. So you see in the colors are more bright here, for example, and at the same time your defect band intensity decreases. So these plots appear more and more dark as you become more and more copper poor. And you also see kind of grainy features here. So you have kind of grain boundary appearing. It looks like a grain boundary where you have a low emission. So you might have lossy grain boundaries, but we are still investigating these films more into the detail and trying to see what these could be. And that study will be out very soon. So as you can imagine, when you have a lower deep defect, as I said, you would expect higher quasi-Fermi level splitting and therefore higher VOC. This is exactly what you see in this plot on the left, which tells you that if you go more and more copper poor, your VOC deficit with respect to QFLS or band gap, if you want to, improves. So it reduces. And for the highest quasi-Fermi level splitting we saw is for the absorber with 0.93 stoichiometry, so CGI of 0.93, which was about 972 millieV. As of now, we have also obtained quasi-Fermi level splitting of 1 volt. So that's quite an achievement. We were quite happy looking at 1 millieV quasi-Fermi level splitting from our absorbers. But this is not what I'm showing today. I'm only referring to copper poor absorbers with 972 millieV quasi-Fermi level splitting. Now, something about quasi-Fermi level splitting. How do we determine it? So we determine it from the photoluminescence as shown in the right, and the physics behind it is actually related to the principle of detailed balance or Kirchhoff's law, which tells you that if you take any body, black body, gray body, it emits a certain radiation, so it has to absorb the same amount of radiation as well. So the emission of the flux should be equal to the absorption flux. And when you disturb or you perturb the system by shining light on it and you move the system from equilibrium to non-equilibrium, it emits a radiation. So the emission is equal to, this is the absorptance of the body, so how much flux it will absorb. This is the black body radiation. So this first term belongs to the radiation flux in equilibrium in the dark, but when you shine light on it, the carrier equilibrium is disturbed and you get this extra exponential factor marked by this quasi-Fermi level splitting term delta EF. So this is just black body radiation equation. If you just plug it in, you get this formula. So the flux from the PL is actually given by the absorptance plus this constant term and this quasi-Fermi level splitting. So one can do the fitting. So if you take the log on both sides, you can fit it and you can actually determine the value of delta EF, quasi-Fermi level splitting. And this is also called generalized Planck's law. So this is how we determined our quasi-Fermi level splitting. There is another method as well, which refers to the calculation of external radiative efficiencies to obtain the quasi-Fermi level splitting, but I'm not going into the detail as the talk is not about that. But roughly, when you are dealing with the absorbers which have very high gradients, for example, then the fitting is not straightforward. Then you need to look at EREs, external radiative efficiencies, and then calculate QFLS from there. Sometimes your fitting temperature, so as I said, I will not go into the detail, but roughly what you see here is you have a conduction band, the valence band, you shine light on it, you split the Fermi levels, so the carrier distribution is not given by one distribution, but it is given by two Fermi levels, quasi-Fermi levels, electron Fermi level and holes Fermi level. Electron goes to the electron selective contact and hole goes to the hole selective contact, and maximum VOC that you can get is the delta EF. So this is a metric of the absorbers. It refers to how good your absorber is, because if your internal photovoltage is good, which means you can extract as much VOC as equal to this internal photovoltage from that absorber. So you want that term to be as high as possible. Now, one last thing before you ask me, did you go even below this CGI of 0.93? Obviously, when we were seeing the improvement, we should have gone, right? If you're thinking about even more copper poor films, think about ordered vacancy compounds and think about CIGS E absorbers. What happens when you make them highly copper poor? You do get the onset of ordered vacancy compounds, which actually helps in passivating interface recombination. But these OVCs exist or do not exist in the case of sulfides, we don't know. Because selenites and sulfides are not equivalent when you look at their thermodynamic stability range, they are not same. For example, when you want to make copper indium 5 sulfur 8 or 135 or 158 count of compounds, 135 is actually doesn't form at all in the case of CIS. And for that, you can look at some papers on the thermodynamic phase diagrams on CIS, CIGS from Alain Lafond. Same thing when you have interface recombination, let's say, then the QFLS is going to reduce, because then your QFLS quasi-Fermi splitting is limited by the interface recombination. So to check that, we try to understand what is the difference between a copper poor or let's say close to stoichiometric absorber, and what is the difference when we take an absorber which is copper rich. So we compared these two because they had pretty similar quasi-Fermi splitting. So we wanted to see what is the difference in terms of interface recombination. So as you can see, you should have spike type configuration in order to have less interface recombination. So you would not want to have cadmium sulfide, but rather something high conduction band, zinc oxysulfide. So we did that. And here you see, so this is the copper poor absorbers on the left, which had quasi-Fermi splitting of 885. Copper rich has quasi-Fermi splitting of 872, pretty much similar. What you see here is that when you replace cadmium sulfide with zinc oxysulfide, your VOCs become as close as quasi-Fermi splitting, which is very good. If this difference of quasi-Fermi level splitting and the VOC is greater than, is positive, let's say, you have interface recombination going on. And that's what you see when you look at the copper rich absorbers. No matter what buffer layer you put cadmium sulfide or zinc oxysulfide, you always get lower VOC as compared to the QFLS. Even though you expect a spike type configuration, but it doesn't solve the interface recombination problem. And that is what is confirmed from this VOC versus temperature plots. So we extracted the activation energy of recombination from these plots, which is given by this extrapolation at 0 Kelvin. And for copper poor absorber with zinc oxysulfide buffer layer, you see this value is close to 1.6 eV, which is equal to the band gap of the absorber. So we can kind of conclude that you have we cannot say the interface recombination is gone completely, but we can say there is a reduced interface recombination. So you have to be again very careful when you look at such plots and they go exactly at the band gap. It doesn't mean you have a zero interface recombination. It tells you have passivated interface defects and there is less interface recombination, but you cannot conclusively say that you have zero interface recombination. And that is what you look at historically. If you refer to the literature of CIGS, it has been done in 2009 that CIGS was made with cadmium sulfide and zinc oxysulfide both, and the activation energies were actually less than the band gap, which means even after replacing an absorber which is from cliff to spike, you do not solve the problem of interface recombination. You can only solve, so you have to switch from copper rich to copper poor. Then only you can solve this problem. So this plot that you see on the right bottom has been done on the copper rich absorbers mostly. That's why the interface recombination limits this activation energy. So it doesn't go to the band gap. So the conclusion here is that if you want to passivate your interface by varying buffer layers, probably it will not passivate it unless you play with the stoichiometry of the absorber itself. So the passivation is composition dependent of the absorber itself, and it's most effective when you are dealing with when you take copper poor absorbers only. So now, so far we did not say anything about the nature of these defects. So we approached to our theoretical colleagues and we tried to look at the formation energy of various defects. So this is the range or the regimes where the calculation was performed. The blue refers to the copper rich domain and the pink one refers to the copper poor domain. This is for CIS, and then the right one is for the CGS. As you can see, for the copper rich area or the regime, you have copper over indium anti-sap defect that has the lowest formation energy, which is given by this red curve right here. So you see, when you are in the copper rich domain, you have this copper indium defect formation very highly likely. Same when you go for the CGS, if you are in the copper rich domain, you have this anti-side copper over gallium formation is very highly likely. And what are their locations in the band gap? So if you look at their locations in the band gap, they are like deep defects, they form deep defects. So you have all the ingredients present to kill the lifetime of the absorber and limit the VOC. So you have this anti-side defects, copper over indium and copper over gallium, which forms in the copper rich domain. So as you move from copper rich to copper poor, what you basically do is you suppress the formation of these two defect culprits, copper over indium and copper over gallium. However, when you move to the copper poor domain, you have the lowest formation energies of this copper vacancy, of course, which is acceptor dopant in your material, indium over copper and gallium over copper. I'm sorry, this is gallium over copper. They form these deep defects and their character is more donor-like. So if you are thinking about more copper poor CIGS, you have to also think about the defect complexes, because in one case you have this acceptor type defects, which are copper vacancies, and if they can form actually defect complex. So it does not mean that if you make copper poor, everything is solved. There is another deep defect is vying for your attention, basically. And as expected, we were anticipating some improvement in the lifetime. So what you see is that you have copper rich absorber, which has a very bad lifetime, which is this green decay curve. If you look at the copper poor absorber, it has a higher lifetime as compared to copper rich. But if you put zinc oxysulfide on top of it, it improves even more. And if I then depict it mathematically with these two different decay regimes, tau 1 and tau 2, I get these numbers, 0.96 nanoseconds and 4.5 nanoseconds, these two. This is what you see in the literature, for example. The highest, or the record absorber, so to speak, has the average lifetime of about 0.6, and here it's slightly higher than that. Although I think taking this kind of averaging of the lifetime makes no sense as such, because these are two different physical processes happening, and taking the average doesn't actually tell you anything, but for sake of comparison, it's okay. And so the bottom line here is that you have a very high non-radiative recombination. Even if your quasi-familiar splitting is high, these values are not at all good as for a good PV material. So they have to be solved. To do that, the first step should be to address these deep defects. So unless you passivate these deep defects, these lifetimes are not going to get improved, because it's ultimately the non-radiative recombination through these deep defects that is limiting it. So this is our best solar cell performance, which was CGI of about 0.93. And as you can see, with zinc oxysulfide, putting anti-reflection coating on top of it, we get numbers about 15.2%. And good thing is we were very happy about the VOC, 900 millivolts. As of now, as I said, we have absorbers with 1 volt quasi-familiar splitting, very high voltages. But the thing is, when you increase the voltages, your fill factor and all sometimes becomes problematic, and then you have to do a lot of optimizations. This is the EQE. Of course, the band gap from here is 1.6 EV from EQE. So we have 15% from 1.6 EV absorber. And that, if you put it in the perspective of losses from various mechanisms, so we have improved substantially this interface recombination by replacing cadmium sulfide with the zinc oxysulfide, thanks to the copper poor absorber. And we have also improved some bulk recombination by reducing the deep defects. So this blue bar is actually less in the case of copper poor absorber. And that actually puts us in the literature somewhere here. This is the regime of interest. As I said, if you want to make a tandem cell with a wide bandgap top cell, this is the area of interest. And you want these numbers to be as high as possible, somewhere here, not here. So this plateau is still frustratingly limiting us, but that's a good sign that we are improving here. So that puts us in from the efficiency perspective, it puts us somewhere here. So these are all the points taken from the literature. And this absorber of 1.6 CV puts us somewhere here. And this particular efficiency that you see right here is from the solar frontier, the record absorber, so to say. And we have also went on to certify our cells. So this is one cell that we certified from Fraunhofer IZ, which was about 14% with close to 1.6 CV band gap. So that's very encouraging. So we not only have absorbers in the lab that are quite efficient, we can actually certify them. And this is where we are at the moment, 14%. So what's next? What should be a possible roadmap? So there is a sun here. When this sun will actually shine on CIGS? This is the roadmap that I can think of based on my research experience. The first thing, obviously, that we should do is the deep defect passivation. And that means we need to understand the chemical nature of these defects. So this is not just about these anti-side defects that you saw today. There is much more going on. And that needs to be quantified experimentally through some complementary techniques. So this should be the first step. And some things that we could try is playing with the sulfur content, because you saw the sulfur vacancy also has a very low formation energy, defect formation energy. It is indeed playing a role. We can actually play with the temperature also, because so far our growth was like about 590, 580 degrees. If you use a glass which allows you to go even higher temperatures, that can possibly help. Then the next step should be, so this is from the capacitance, the doping density of the copper poor absorbers are actually low because of the compensating defects, indium over copper, for example. Need to improve the doping density, and for that, a lot of things have been done for selenides, but not at all for sulfides, which is like alkali treatment. And also silver doping, for example, that is showing quite encouraging results in casterides and also for selenides by reducing the band tailing, which is not limiting here, but it does play with the doping density as well. So it could be useful. Then these gradients of the gallium gradients to improve carrier collection. And this is also something that has been extensively done for selenide absorbers, but not much do you see on the sulfides. So I think gallium grading also something that will come at one point that can be improved. And then grain boundary passivation. So we are getting some hint that the grain boundaries are actually lossy from the CL studies, and we are doing more extensive studies on that. And you will soon probably read something about it. And there also you can think of something sodium, potassium, or cesium passivation, like alkali passivation, the grain boundaries. And then only you can think of putting your absorbers on top of a TCO. So this is one cell I made on top of a ITO glass, for example, and which has a very nice transmittance. You can see through, good for, but the cells who are shunted, not at all good. So this step will only come when you overcome all these limitations, and then you should jump on the TCO, and then a trophy is waiting for you. So this is the rough roadmap that I can think of, possibly for in the future for CIGS. And we should not give up on CIGS. 15% efficiencies, and the QFLS higher than 1 volt is quite encouraging. So I think there is still a lot of room for improvement. With this, as I said, it's very promising. So we spurred some activities at IMEC when I joined here in. So I was involved in several project proposals here, for example, one that I recently received as a Marie Curie postdoc fellow, and that is on the solar to fuel conversion using CIGS, wide bandgap CIGS, and the bottom cell, that is silicon, to drive CO2 reduction, for example, because you can make the CIGS wide band gap, 1.7 EV or 1.8 EV, depending on how much gallium that you put. This could be quite a promising strategy to go towards other application like CO2 reduction. Another project that I'm involved in deals with the casterites. So that's again a new project that has been granted very recently from Miranet Horizon, where we are using casterites to split the water. So creating hydrogen molecules from the casterite absorbers. And we are also working on tandem applications where we are working on perovskites and CIS, perovskites and silicon. And here we are developing a tandem system that has a perovskite top cell and the bottom cell is CIS. And we are getting some good preliminary results from this as well. And this we are making both like 4-terminal and 2-terminal. So both the options we are pursuing. And we also have a recently approved proposal, CETA, where we'll be working on complete stable inorganic tandems where there is silicon and CIGS top cell for PV. So both are kind of related like CETA and this one, but the application is pretty different. So with that, this is the end of my talk. Thanks for the patience for listening to my talk in the evening hours in Sydney. And I want to thank Professor Susanne Ribbentrop at University of Luxembourg, who was supervising this research, and my colleagues there. This is the LPV group. And this is the photo back then. The masks were not trendy. It was the helmets that we were playing with, not the masks. And then I also want to thank our expert partners from University of Cambridge, Professor Rachel Oliver, who helped in the Catheter Luminescence, Professor Geoffroy at Leuven, now he's at Dartmouth College, who helped us in theoretical calculation and some elemental analysis at Luxembourg Institute of Technology. And I would also like to thank Professor Bart Vermang at IMEC, with whom I'm working now, for all the proposals that I wrote and got recommended. So very thankful for that. And I'm really thankful to your attention. And keep in mind that, and I also want to thank the funding agency, FNR Luxembourg. So reduce your carbon footprint. So with this, I would end my talk and are most welcome.
Okay, thank you so much, Dr. Shukla. I can see it's a very comprehensive understanding of the high bandgap CIGS. Actually, I think we can first take some questions from the audience. I think they might have some question to ask you because some of them also working on similar project. So from the audience, if you have questions, could you please unmute yourself and like ask a question? While we are, yeah, I can see Eric.
So, hello. So, thank you very much for a very nice talk. So it's very comprehensive and very interesting. So, so we are so excited to see this wide bandgap CIGS moving forward. So I have a few questions on your talk. So, so may I ask, first you have mentioned you have recently measured the quality Fermi level splitting around 1 volt, right? So that's really encouraging. So, but you said when the voltage get higher, you have encountered some problems in terms of the fill factor. Yeah. So can you tell more about this? So what's happened to the fill factor?
Yeah, so what happens is that when you increase the band gap, because we are doing this co-evaporation process, so having an identical film in all the runs, sometimes it's difficult because it's pretty much machine dependent. Sometimes the condition, you have all the sulfurs that's condensed, so you have to clean time to time. So conditions can change time to time, but I think it is mostly related to the buffer. So you have to optimize the buffer layer according to your absorber, and then you can improve the fill factors. What we do notice that if you go to lower copper poor CGIs, even less than 0.93, we see a lot of instability, meaning light soaking effects, and also the absorber degrades very quickly. So 0.93 is probably an extreme composition where we are kind of balanced. If we go even more copper poor, I think we create problem of instabilities, like metastability in the case of selenites. But I would refrain myself to say something similar to sulfides because I don't have any evidence yet. But something like that happens. You create some sort of metastabilities. But I won't say these are metastability effects similar to selenites.
Okay, so are you speculating there's some kind of OVC formation at the back or something can decrease the field?
Yeah, so I have some backup slides here. So I think you are familiar with this particular phase diagram. It's from this Tomere, from Alain Lafond, which tells you that if you move from copper sulfide to indium sulfide line, you do not have the formation of 1,3,5 compound. You see copper 3,5, but you do not get 1,3,5 formation in the case of indium films. So saying that you have a similar OVCs as compared to selenium, I would not say so, because there is something fundamentally different when you compare selenites and sulfides. But if I checked some Raman measurements, which I'm not showing here, there were some hints that probably there is a formation of such ordered vacancy compounds. And for that, I would highly recommend you to read a recent study from Professor Robert Kawa called copper indium disulfide. So that is done on pure single crystals, where they are talking about the formation of defect complexes, which comprises of copper vacancies plus indium over gallium anti-side defect, which is a donor defect. It forms a complex.
Okay.
But I restricted myself because I didn't have any experimental evidence, so I restrained myself commenting on that.
Yeah, thank you. So can I ask another question on because it's so nice to see the certified result of the 14%. So I have noticed there's some kind of heterothesis when you sweep forward and backward. There are some difference. So what's happened? So can you explain?
Yeah. The high efficiency cell that you saw, as I said, we are actually at the extreme of the composition where you start seeing very noticeable light soaking effects.
Okay.
So the JV was obtained after light soaking for 15 minutes, and that's why they used the similar protocols what they use for perovskites. So Fraunhofer IZ, they asked us whether do you have instability, this light soaking effect. So they applied the same protocols as they used for perovskites, and that's why they show this hysteresis.
Okay, it's not much. It seems it's a tiny bit.
Yeah, it's tiny bit, but it is there, which you don't see for selenites. Only after perovskites these things are into the attention a lot. So they did it, and it's nice to know that something similar happens here also. It's related to the light soaking effect.
Okay. Okay, thanks. Thank you.
Okay. Do we have other questions from the audience?
I do have another question. Congratulations on the results, and also this is Xiaojing from SPREE at UNSW. I think it's really very good results. But another thing I just want to say, also congrats on the success of the CETA project on the European one. So I think that's a really great success. So I guess during the proposal application, I'm not quite sure whether how we going to address indium issues. Do we have any have you ever thought of that part?
Can you repeat your question on indium?
The indium, for example, for the ITO, a lot of people mention about the ITO going to be some sort of a sustainability issue, and I think that's also the reason it comes to the next generation cathode instead of a CIGS. So that's for the lower bandgap CIGS has got that problem. So I think for the high bandgap one, you're also going to have that problem. So have you thought about for the indium? A supply issue, anything we can do here?
That's true, and I have encountered these questions a few times. And what I will refer it to here is a recent white paper, some study that says it will not be a limiting factor. But I think it will be a limiting factor if you go for a large scale. But then I think recyclability would become very important. So if we manage to recycle it nicely and we can reuse it again, that could be a sustainable strategy, I believe. But certainly that seems like a bottleneck right now. But I think from recyclability, we can address this issue. But I'm not 100% sure that in the long run, how this problem will actually turn out.
Yeah, just a following question of that one. I think like recycling of the indium definitely is going to be something sort of like a solution for the long-term sustainability, particularly for the terawatt level deployment in the future. So have we like really check about this one? For example, for the high bandgap cathode and the low bandgap cathode, actually we found like our absorption coefficient of the high bandgap cathode is higher than the low bandgap one. Have we like a check about the absorption coefficient of a high bandgap chalcopyrite compared with the lower bandgap chalcopyrite? So do we really need that thick absorber materials in the high bandgap case?
Yeah, that's a very valid question. When we go for that's a very valid question. So for castorites, you have a high absorption coefficient, so you use less material in the end. But I would think that the absorption coefficients for the CIGS disulfides are actually not that low. So you can still go even thinner.
Yeah.
And when you use as a top cell in the tandems, these cells can be more thin because then you have a bottom cell that will be absorbing the light. So I think, yeah, they can be made much thinner. But right now we are making it thick because these materials haven't proven themselves up right now. They are still in the stage of being promising than actually promising. So once we break the barrier of 1 volt experimentally, like quasi-familiar splitting is fine, but once we get an absorber with 1 volt band, 1 volt VOC, that will be something. Yeah.
Yeah, great. Thank you.
Thank you.
Thank you. Any other question from the audience?
Yes,
okay.
Yes, I have a question.
Yeah.
That from SEM and results, we can see that even though in Cooper poor condition that your grain size is large and you have formed a quite flat surface, have you ever experienced, because indium is quite easy to accumulate when heat treatment or sulfurization process, have you ever experienced indium accumulation on the top surface that make the morphology quite rough or before? And if so, how do you control it?
Yeah, so thanks for asking this question. Actually, I want to highlight here that when you do a 3-stage evaporation, the way we control the final stoichiometry is by playing with the duration. So when we do a longer duration third run, we get a copper core absorber. So remember, you have a longer annealing times as well, because when you do a longer run, you are effectively annealing the absorbers for a longer time. That can actually contribute to the grain growth. We don't know. We are actually studying on that from catheter luminescence recently. And to answer your other question, did we check the accumulation? So I do have something for you, which is here, let's say, yeah, here. So at the front surface, we do have a high gallium because we are evaporating gallium in the end, which actually helps us. And it also drives the sodium crazy high at the front surface, because when you have a copper poor surface, the diffusion of sodium is faster. That also might be helping us. We don't know. So these are all the things we need to quantify. So we do see a segregation of gallium, not the indium at the front surface. Actually, that's what we see from our SIMS results. So this is from the SIMS. And yes, the morphology becomes rough and there's some sort of recrystallization going on, which we are still studying from catheter luminescence mapping. We are actually checking the grain boundaries and within the grains, if they are striking, if the different absorbers with different copper compositions are strikingly different in terms of crystal quality. We are investigating this at the moment, but there is a segregation of this gallium species at the surface. Yeah. Which might not be good, by the way, because then you can have a barrier for electron flow. So that also needs to be played in the end. This needs to be controlled when you are doing synthesis.
But you don't see the indium segregation?
That I don't see. I mean, at least from the experimentally, I don't see any indium segregation at the surface.
Okay.
Okay, great. Thank you.
And I think that has to do with the diffusivities of indium and gallium within the copper poor matrix. CIGS.
Okay. Thanks. Any other question? Actually, I have one about the green boundary you were talking about. You said the CL emission from the green boundary and the green interior is different.
Yeah.
And you propose to use some alkali elements to pass with the green boundaries.
Yeah.
Could you tell more about that? How do you determine the green boundaries and the green interior difference? And do you see the positive effect of the alkaline element persuasion?
So actually, an extension of this study, what we have done is that looking at the line profiles in the cathode luminescence. So when you go from one grain to the other grain, you see a shift in the CL spectra. So you have a lower band gap emission or lower band edge emission coming from the grain boundary, which we think is could be due to inhomogeneities, or it could also be from the tail states at the grain boundaries, which could be resulting in the red shift of your CL spectra. So these are this is the observation we have so far. After quantification, we think it's both. So you cannot rule out the non-homogeneities, because there could be gallium somewhere high, somewhere low, could be resulting from, which could be giving to these shifts. And there could be these tail states because of the high compensation. You have those tail states because, let me short myself up. I have also done a recent study on the stoichiometric absorber. And if you check that study, I have shown that there is a potential fluctuations going on in the stoichiometric absorber, which means you have a high degree of compensation. So at the grain boundaries, you can have high band tail recombination for stoichiometric absorbers if you have a very high compensation, which is the case for copper poor. So that study we are still finalizing, and I think very soon you will see that.
Okay, great. Thank you. Thanks for your time. If we don't have further questions, we should close today's seminar. Thank you very much, Dr. Shukla. It's great talk, and we learn a lot from you. Hope in the future we can communicate more frequently, and hope in the short term you can present your work or visit us in person. And thanks everyone for attending this seminar. Now let's close today's seminar. Thank you.
Thank you very much, and have a nice evening, everybody.
You too. Thank you.